Hello everyone. So today in this video we'll be discussing Leetcode problem 436, find right interval. Before moving on to the actual problem, we'll be discussing a little bit about binary search and what things we can keep in mind before deciding whether binary search will be applicable on this question or not, and what properties need to hold to be able to apply binary search. Then we'll try to apply binary search on this particular problem statement, and finally we'll move on to the code for this question, and we'll try to write the code and submit it on Leetcode and see. Okay, so let's move on. So first let's discuss about binary search. Now the gist of binary search is that we are given a sample space, and in this space our answer might be present or might not be present. Now every time in binary search, we pick a particular value from the sample space and then decide in which direction to move from that particular value. Now, at every step, what we do is we take this decision and decide one particular direction, and then we discard the complete sample space in the other direction. So every time we divide our sample space into half of what it was previously. Now, why we are able to discard the other half of the space. Now the very simple property that each element in this space is following is the monotonic property. Mm, Now monotonic property, because all the values which are present or all the elements which are present in this space are following this particular property in particular direction. So if I say in terms of magnitude, so if I have taken an array of say 5 numbers which are 1, 4, 8, 10 and 20, so I know that as I move towards the right, the values are strictly increasing in this case. Now if my values are strictly increasing in one direction, I know that if I need to search a particular number, if I'm at a particular cell right now, say I'm at 8 and I need to search a particular number, say 40. Now I know since the values are following a particular trend in one particular direction, that is values are strictly increasing in right, and the value that I need to search is greater than my current value, which is 8. So definitely I'm going to find my answer on the right side of 8 and not on the left side of 8. So I can very easily discard this complete left side and begin to search in the right side. Now this monotonic property is not necessarily in terms of magnitude. So here it is in terms of magnitude, but there might be other properties, and the sample space might be following that property uh, in a particular direction. So if I say if it would have been an array of say strings, then the monotonic property would be that the number of vowels in each string is increasing as I move towards the right. Or if this array represent if this array contains the start node of a graph, then I can say that for each element which is the start node of a graph, the size of the graph is increasing as I move towards the left, towards right. Now, and when I say this sample space doesn't is it is not necessary that this sample space will be represented by an array. This can be anything. This might be an array, this might be a matrix, or it might not be any container as such. So if I say that the set of whole numbers or the set of natural numbers or integers, they this set in itself is also following a monotonic property, and here the property is in terms of magnitude. So as I move towards the right, the magnitude is increasing in this set. So there are type of questions where we try to find the answer to this question, to find the answer to that problem by doing a binary search on the set of whole numbers or integers. So that might also be the case. So whenever we are trying to apply binary search, we must need to make sure that the problem we are applying it on, that there is some kind of monotonic property being followed by the elements of that container. If the monotonic property, if we are able to identify this monotonic property, then basis on this property we can form the conditions of our binary search and apply binary search, and based on this property at every step we can discard half of the sample space. Now, discarding half of the sample space, what benefit does it give? If we do a normal linear search, then we have to check every element and the complexity is O of n. But since at every point we are discarding half of the sample space, so if I'm at 8 right now, I do not need to check any value on the left side. So this saves a lot of time, since at every step I'm not checking half of the elements of that particular size. I mean, half of the elements at the time I'm at an element, I'm not checking half of the remaining elements. So every time my search space is decreasing by half, so it is like the size is initially n by 2, then it's n by 4, and so on. And one more thing I would like to add here. So as we discussed that the elements would be following a monotonic property, now this property does not need to be a strictly monotonic property. So what I mean by that is, if for instance, like if the elements of an array are increasing in a particular direction, they do not need to be strictly increasing. Now, they can be values which are equal, but they once I've got a value, there should not be a value smaller than this value on its right, if the monotonic property under consideration is the increase in magnitude. So I can say that it needs to be monotonic but not strictly monotonic, and this will determine what conditions we are using in our binary search code. So depending on what the property it is following and what the problem is, our conditions in the binary search code would be modified. Now let's move to the problem statement at hand. So we are given an array of intervals where each interval is represented by a start and an end, and each start is unique. And a right interval is defined as an interval j such that the start of j is greater than equal to the end of I, and start of j is minimized. So if I have an interval I, the right interval for this interval I would be an interval j. Now interval j could exist before interval I in the array or after interval I in the array, and the property j follows is that the start for interval j should be greater than equal to the end of interval I, and start j is minimized. So there might be many intervals whose start might be greater or equal to the end of I, but we have to select that interval for which this start is the minimum, and we have to return an array of right interval indices for each interval I. So if we have given an interval array of say 4, then we have to return an array of size 4, and each index represents the index of the right interval for that particular interval. And if for a particular interval there is no right interval in the given array, then we just put -1 at that index. So first of all, let's try to understand the question in a little more detail using an example. Now, this is the input array, and this input array has three intervals. Now, the output would definitely be an array of size 3. Now, for this particular interval, the start value is 3 and the end value is 4. Now, I need to find an interval whose start value is greater than equal to the end value of this interval. Now the end value is 4 here, and for the other intervals the start value is 2 and 1, and none of these is greater than equal to 4. So for my first interval, I have no right interval, so I'll just add -1 in my output array. Now for the second interval, my start value is 2 and my end value is 3. Now I need to find an interval whose start value is greater than equal to 3. Now for this particular interval, which is 3, my start value is equal to its end value, and this interval is useless. This is of no choice. This is of no use. So I'll choose this particular interval as the right interval, and I'll add its index to the output array. So I'll add 0 here. Now moving on to this particular interval. Now the start value is 1 and the end value is 2. Now the start value for this interval is greater than its end value, and the start value for this interval is equal to the end value. Now both these intervals are candidates for the right interval of this particular interval, but I need to select the one with the minimum start value. So out of 3 comma 4 and 2 comma 3, 2 has the minimum start value, so this interval becomes the right interval for this interval, and I add the index for this interval to the final answer. So I add 1 here, and this is my output array. This is the array which I need to return here. Now since we are done with the explanation, let's try to identify how can we apply binary search in this question, or why should we even apply binary search in this question. Now what I know is that I need to search an interval, and the interval is being searched on the basis of the magnitude. Now if all these intervals would have been in a sorted order, then the values for each start would have been in a strictly increasing order. So if these intervals would have been sorted, then it would have been 1 comma 2, 2 comma 3, and 3 comma 4, since the start values for each interval is unique. So this would have been in a sorted order. Now I could have picked each end value one by one, and I could have just applied binary search on the start, since start values have a monotonic property and are strictly increasing in one direction. So I could have just simply applied binary search and checked. So like for instance, if I am checking for 3, I would have first checked at this place. Now this is the same index, uh, and also I can see that 3 is greater than 2. So definitely on the left hand side I am not going to find my answer, because these are sorted on start index. So I need to move on the right hand side, so I can completely discard my left hand side and move to my right hand side. So using this monotonic property of magnitudes, I could have easily applied binary search. Now these are not sorted. So if I'm at right now at this index and I'm searching for 3 only, so I cannot say whether I'll find my answer on the left or on the right, and here the answer is on left, so it's not even on the right. So here I cannot decide. Now one thought can be, why can't we directly sort this array and then start applying binary search? Because the final output which needs to be given has to contain the original index of the interval. So if I'll apply binary search, these would get these intervals would move to different indexes as compared to their original index, and then this output array would also get modified and it would not be according to their original index. So to overcome this problem, what we can simply do is that we can every time when we need to preserve an index and also apply sorting, we just take a sample, we just take a helper array and in the helper array we insert elements along with their index. Now I can simply sort that array, so it would be sorted on the element, but the index would also be preserved along with the element. So if I make a helper array with the start values and their original index, so it would be 3 comma 0. I'm not adding end values to this helper index to save space, because I'm only doing a binary search on the start values, and I need start values to be sorted, so there's no point of adding end values to this. So the second value would be 2 comma 1, and the third value would be 1 comma 2. Now I can simply sort this array, and after sorting, my array would be 1 comma 2, 2 comma 1, and 3 comma 0. Because when we sort, the first it is sorted on the initial values, and then it is sorted on, if the initial values are same, then it is sorted on the second values. But since all start index are unique in this case, so it'll always be sorted for on the first element. The second element would be considered here for sorting. And again, if I need to search for this particular interval, so I'll take my value 3. I'll first check with the middle value. Now 3 is obviously greater than 2, so I'm not definitely not going to find my answer on the left side. So I can simply discard this and I'll check on the right. Now 3 is equal to 3, so I have found a match, and uh, I found a match. So if there would have been other values as well, like 4 comma 0 and 5 comma 0, so I would have, sorry, 4 comma 3 and 5 comma 4, because the index cannot be 0 again. So I would have first searched with 4 comma 3, and I know that 3 is less than equal to 4. So this is a candidate answer, but I still need to check on the left because I need to pick an interval with the minimum and if there's an answer. So this has been discarded. Now at this point, this would have been discarded. So this would have been my search space. I would have compared with it, and 3 is equal to 3, and 3 is also less than 4. So now this becomes the answer. And since we have searched we have kind of searched the whole space, because we have discarded half and we have searched in the other half. So now I'll finally return this as the answer. And I have the original index. So this was present at 0 index. So I know that in my answer, 0 would be added at that particular index. So this is the way we can apply binary search in this question by following the monotonic property of magnitudes here. So let's write the code for the solution that we discussed in the previous slide. Now, first of all, we need to make an array of the start indices of each interval along with their original index in the array, and we need to sort it based on basis of their magnitude. So let's start. So I'm only adding the start for each interval as we discussed earlier, and not the end, because we do not need the ends in a sorted order. Now what we'll do is that we'll iterate through the intervals array. We'll pick each end for each interval, and then we'll do a binary search for that end in this sorted array. Let me make a final vector that I'm going to return my answer, and the size for this would be same as my original given input array. Now my end is equal to intervals of I of 1, and my binary search limits are 0. I usually use start and end. So what should I use? Start and end val, and it is end. Okay, so this is basically the size of my sorted start minus 1. Current answer is basically int max. So we'll update the answer in this current answer. Now a normal binary search loop. So while my start is less than equal to end, int mid is a basically start plus end. So I'll check with the middle element at every point, and based on the value of this middle element, I'll decide in which direction to move. So sorted start mid dot first is greater than equal to end val. So if it's greater than equal to end val, then this is a potential answer. So I'll update my current answer with mid. So not directly with mid, I'll do a min of current answer comma mid, and then I'll check on the left hand side because I found a potential answer. Now all the smaller values would be on the left hand side and nothing on the right hand side. So I'll decrease my end with mid minus 1. Now else if the value is greater, then I need to check on the right hand side because there would be nothing on the left side. So mid plus 1. Now once we are done with binary search, if my current answer is not int max, then I'll update my answer as answer of I is equal to sorted start current answer dot second with the original index of that value, and then I'll return my answer vector. Let's run this. Okay, so the test cases, the base cases passed, and it passes all the final test cases. So yeah, we should be good to go with this code. So with this, I'll end this video. As usual, if you have any queries or any doubts, please do mention in the comments. I'll try my best to address all your queries and hope to see you next time again. Stay safe and keep learning. Bye.